This lecture is about rolling. So this involves the application of Newton's laws both for linear and rotational motion. So we are going to see pure roll, also called a smooth roll. So this means no skidding and sliding. We'll see then the kinetic energy of rolling, and then we will look at the rolling. So this is what we need from previous lectures. So you may look at my lecture on rotation, the kinematics of rotation, and we have established the following formulas. So as the distance on this piece of circle is s equal r theta, we have the velocity, which is tangential. We have a tangential component of the acceleration, which is r alpha, and a centripetal acceleration, which is either v squared over r or r omega squared. And omega is a vector represented in this case by a vector out of page. This is the case of uniform rolling. So it's a uniform motion. So we define by P the contact point of the wheel with the rod. Vcom is the velocity of the center of mass. Okay, and the center of mass is, of course, the center, in this case, of the wheel. We call this O, the center of the mass, the center of the wheel. So this wheel is rotating with this angular velocity clockwise. So it's a uniform motion. That is, if you look at the forces on the wheel, there is none. So F net equals 0, which means ma equals 0, therefore no acceleration. And therefore we don't have any forces, so we have no frictional force acting on the wheel in this case. Let's take a look at the case where there is an accelerated motion. So accelerated motion means there is an acceleration, Acom. And if there is an acceleration, it means there is a force. So in this case, the only force, horizontal force, is the frictional force, shown here. So let's take the case where a wheel is being made to rotate faster. So the faster rotation tends to make the bottom of the wheel slide to the left at point P. So the wheel exerts a force on the road going on the leftwards. Therefore, as a reaction, the road exerts a force on the wheel towards the right. So this Fs here is the force exerted by the road on the wheel. And of course, it has the same direction as the acceleration, because ma equals Fs. And of course, this frictional force is a static frictional force, because there is no skidding and sliding. So if the wheel were made to rotate slower, so we would have an acceleration in this direction, and therefore Fs would also be in this direction. So let's look at different point of view. In this case, we have the velocities relative to the center O. So imagine you're on the wheel at O, and what you see is just a rotational motion. So all the velocities on the rim here are the same, and their magnitude is the radius multiplied by omega. Okay, this is the magnitude of the tangential velocity. So now with respect to the road, so it is this, it turns out that the rolling is in fact a rotation, so the wheel, the entire wheel is rotating about point P, the contact point. So if you take a point, let's say here, an arbitrary point on the wheel, the velocity will be given by this vector, so it will be perpendicular to the line going from that point to the axis of rotation, by definition of rotational motion. Okay, so we get all these different kinds of velocities, and you will notice that this particular point has no velocity at the contact point. Okay, so let's establish some properties of rolling. Here this wheel has progressed from this position to this position, and we have the point P, contact point, has moved from here to here, and the center of the wheel from here to here. This can be obtained, so the wheel has turned, let's say, by an angle theta. Therefore, this distance is s equal r theta, and it is the same as this one. Okay. So this distance is r theta. So just a remark here, this is also typically used when you study pulleys. Okay, because when you pull a pulley, let's say, has rotated by angle theta, the rope has moved by this distance. Alright, so let's establish the velocity of the contact point P. It is ds dt, or d theta dt, and d theta dt is omega O, so it is this omega. Okay, by definition of the rolling. So we know that P and O move exactly the same way, like this. So this velocity is also v of the center of mass. And v of the center of mass can be viewed as, so if you consider that this wheel is rotating about point P, as we have seen just before, this Vcom can be, the magnitude can be r multiplied by omega of rotation about that point. So it's r omega p. But since r is the same, we have omega of rotation of the wheel equal omega at that point, p. So this is shown here. And this is, so these are two properties that you have to remember when we study rolling, that center of mass and the contact point have the same linear motion, and that the angular velocity about center of mass is the same as the angular velocity about point P. Alright, so here we have again that rotation about point P. We have s equal r theta, we have v equal r omega. So let's look at the instantaneous speed at point O. So it is Vcom in fact, but Vo equal r omega p about that point. The instantaneous speed at t, that point up there, is by definition of rotation about point P is 2r, so this length, multiplied by omega p. Alright. So this is something sometimes useful. And okay, we have just established also before that Vcom equal r omega. So this is something to be remembered. Very useful when you need to solve problems. Alright, so in a previous lecture I've showed you that the reason for studying pure translation and then pure rotation is because any complex motion can be represented as a sum of a translation plus a rotation. And the rolling is an example, very simple example. So let's look at this. So we have here rolling. So we have seen that this point is moving at velocity Vcom and that one at velocity 2 Vcom. Okay, that particular point, because it's rotating. So we can represent this complex motion as the sum of two very simple motions. So the first one is a pure rotation. So pure rotation with rotational velocity omega means this point is rotating at Vcom, because it's r multiplied by omega, and Vcom is r multiplied by omega. Right, this one also, it's also Vcom, but in the other direction. Pure rotation. Now let's look at pure translation. If this wheel is just moving in translation, so no rotation at Vcom, so any point on that wheel has the same velocity Vcom. Okay. In particular, this point and this point are moving at Vcom, and this one also. So if we just sum the velocities for all the points in this wheel, so this one plus this one, we obtain that. So let's take this point in particular. We have Vcom plus Vcom indeed equal to Vcom. The center, this one is not moving, the center is not moving. This one is moving at Vcom, therefore the sum is Vcom. And this one, we said it's not moving, instantaneous, velocity is 0 here. Indeed, we have minus Vcom plus Vcom equals 0. So let's now look at the kinetic energy of rolling. We can use that principle of superposition again. So what is the kinetic energy of rotation? We've seen that it was half of I omega squared, and I of the center of mass. The kinetic energy of this in this one in linear motion is just the usual half of mv squared, and the kinetic energy of rolling is therefore just the sum of the two. Alright, so you see how easy it is to use that principle of superposition. We could have calculated that kinetic energy here by just considering this and calculating the kinetic energy of several points. And we will do that just now. So here I just would like to summarize. A rolling object has two kinds of kinetic energies: a rotational kinetic energy and about its center of mass, and a translational kinetic energy due to the translation of its center of mass. So let's now calculate directly the kinetic energy. So in fact we have this system in such a case. So definition of kinetic energy: this is a rotating object about point P, rotating about point P, therefore it is given, the kinetic energy is given by this, and this is IP, rotational inertia about point P. And you see that is not a usual point that we choose to calculate I. Usually we choose a symmetry axis for such a thing, so this is going to be a bit difficult to calculate. So how can we calculate it easily is to use the parallel axis theorem, which states that IP will be equal to Icom from this point plus m total mass by the distance, which is in fact here r. Right, so we have IP equal Icom plus mr squared. we replace this in this expression, so we'll have two terms. The first will have Vcom, and it will be just half of Vcom omega squared, and the second will be a half of mr squared omega squared. But you know that V equal R omega, therefore we get half of mVcom squared for this term. And we get the total kinetic energy, of course the same result as before. Okay, now second problem. Let's find the acceleration of an object rolling down a ramp or an incline. So first of all, let's recall the problem of a block not rolling down a ramp. So does it depend on the mass, on the size? So let's first establish that acceleration for a block. So this is our block, center of mass is here, we have a nice incline, and we decide to have an axis x designed like this. So this is only translation. So let's look at the acceleration is coming in the equation of Newton's second law, so just let's write it. So we need to know the forces on the block. We have the gravity, normal force, we may or may not have a frictional force, kinetic force, because the block is moving. Okay, so we will look at the forces along x, because that block is moving along x, of course downwards, but along x, so only the forces along x will be useful for us. Okay, so we can decompose the gravity into two orthogonal forces like this, and we can write the linear form of the second law of Newton. So x is oriented positive upwards, so we have Fk positive and minus mg sine theta, called ma. So okay, so Fk can be expressed as in this way. You should have seen that in linear motion. So in the end, our acceleration is given by this. Already you can see that there is no straight dependence on m, even though this may include something, but this mu k is empirical. Okay, of course the friction comes from fundamental forces, but it is very complicated, so F is in fact an empirical force in order to take into account all the friction taking place between this block and this incline. So just let's say there is no friction, so we have only fundamental forces and theory in this expression here. So we have only m minus g sine theta. So we have no effect of the mass and the size. So this is interesting. No effect of mass, which is in fact linear inertia. So okay, so now we can look at rotational motion. So now we have some circular object going down. So we have again gravity, reaction, and we need friction this time. Static friction, because without friction this wheel would just go down like the block without rolling. So we need static friction if we want this to roll down. So now we have a rolling object, so there is translation and rotation, so we will have to use Newton's second law in both linear and angular forms. So let's start with the linear form. It's very similar to the one we had just before. So there is Fs plus gravity equal Vcom. So let's look at now the angular form about the center of mass here. So it's tau net equal I alpha. So what are the torques on this wheel about point the center of mass? So you see that this force Fn, gravity, both are intersecting this axis of rotation, so they produce no torque on the wheel. However, the friction does produce a torque, and it is the magnitude of that is Rfs. So we have Rfs equal Vcom alpha. So we choose the convention for the sign convention. So we choose a plus for torques producing rotation in this direction, which is the case. Okay, so we have a plus here. So let's examine this. We have Vcom that we want. We have Fs alpha. So three unknowns. We need a third equation. So we can get that by relating linear and rotational motion. We know Vcom equal R omega in magnitude. Okay, R omega. And we have a minus here because it produces a rotation in this direction. And Vcom, so omega is also in this direction, and omega is positive because we have chosen this as a positive direction. But Vcom is a vector, and it is in this axis x, and the positive direction for the axis is up, but Vcom is oriented down because the wheel is going down. Therefore, we need this minus here for the magnitude. So we have also, so we take the derivative of Vcom, so we get Vcom equal minus R alpha. So now we have enough equations we can solve. So let's start with 2 with 3. So we can get rid of alpha. In such case, we get this equation. Next step, we want to get rid of Fs. So with 1, okay, we replace this expression in this one, and we get our final acceleration. Okay, this nice expression. So let's look at this expression in more details. It is represented here. So we have Vcom, and we have mr squared. So this is also, this is a rotational inertia, and this is also a rotational inertia. So it's a mass by length squared. All right. So this has no unit, in fact. Nevertheless, there is definitely an effect of inertia in this system, because it will depend on whether we have so it's a circular object, but it can be a sphere, a hollow cylinder, or a solid cylinder, for example. And all these have different rotational inertia, so they are represented in this column. So here is if we replace this in this expression, we get the acceleration of the center of mass, and our acceleration here do not depend on the mass of the object as for the block, but there is this number here comes directly from the rotational inertia. So rotational inertia is important in this case. So the rank here is the amplitude of the acceleration. So this one is greatest, then this one, and this one is the smallest. And it rank opposite to the inertia. So this is the last here. This one is the greatest inertia, then this one, and this one has the least inertia. So if you make do a kind of a race, so if you take a sphere, solid sphere, hollow cylinder, and a solid cylinder, and you put them at the top of a ramp and you let them go, they do not arrive at the same time at the bottom of your ramp, and the sphere will arrive first, then the solid cylinder, and then the hollow cylinder, and this is because of the inertia. The greater the inertia, the longer time it will take to reach the bottom of the ramp, because again, inertia is resistance to change. So the greater the inertia, the greater the resistance to the motion. And so this explains why the sphere will arrive first, then followed by a solid cylinder, and then the hollow cylinder. Another point is that all accelerations are independent of the total mass and the radius. So it's quite interesting if you take, let's say, two solid spheres, one very small and one very large, and you just let them roll in the same conditions, they will arrive at the same time at the bottom of the ramp, even though one could be very much more massive than the other one. This is the formula summary for this lecture. So we have seen pure roll as a combination of pure rotation plus pure translation. So we have this distance traveled by the contact, or the point of contact, or the center of mass. Velocity of the center of mass is r omega, and this is the kinetic energy.